So today I'm going to talk about our process nucleosynthesis, which is about how heavy elements are made. So my name is Hong Chi Hong, and this is my SID. So here are the table of contents. First, I'm going to talk about the mechanism. I'm going to compare the R process and S process nucleosynthesis. I'm also going to talk about some of the astrophysical sites, which are the possible candidates for our process to occur. Some of the nuclear physics behind the R process nucleosynthesis, and some of the future directions for the R process nucleosynthesis research. So, what is R process nucleosynthesis? So, R process nucleosynthesis, the R stands for rapid. It's a rapid neutron capture process, and it's responsible for the creation of approximately half of the atomic nuclei heavier than iron, which is so-called the heavy elements. And the other half, they're by the P process, where the P stands for proton, and S process. S stands for slow. So, the key idea about whether it is rapid or slow is actually to compare between the neutron capture rate and the beta decay rate. So for our process, which are rapid, it means that it has the neutron capture rate is faster than the beta decay rate, which means that for a seed nuclei, it's gonna capture the neutron, and by the time it capture it, it's so fast that even beta decays that hasn't occurred. So beta decay means that the neutron it's going to decay into a proton, an electron, and an antineutrino. So that means it can trap and capture the neutrons inside. So for our process, the isotope they have short half-lives in comparison to S processes, which have long enough half-lives to be studied in the lab. Our process is very rapid. It's around 100 neutron captures per second, whereas in contrast with S process, which is about neutron capture every 10 to 100 years. For our process, they can create their own C nuclei. So that this process, it can proceed in a massive star, which has no heavy nuclei. But for S process, it is a secondary process, so it must have some pre-existing heavy isotope as C nuclei, and it can convert into other heavy nuclei. So here I'm going to talk about a bit of the R process mechanism. So at the start, um, there should be one or more heavy C nuclei, which is perhaps the isotope, and then um, the reaction is going to occur until the abundance peak, which is typically centered on uh, iron 56. And then it's going to occur with a lot of rapid capture, which should be faster than the radioactive decay, such as beta decay. So it's going to occur uh, all the way until the neutron drip line, which is basically the stability limit governed by the strong nuclear force. Because uh, in reality that any isotope when it tries to capture more neutron, there's a limit where this strong nuclear force, which is short range, can contain that many number of neutrons. So you can see on the right, there's this diagram which shows for R process and S process. So you can see, let me see. So you see here for the R process, because it can capture a lot of neutrons. So you see on the x-axis is the number of neutrons. It captures neutrons very fast. So you can capture a lot of neutrons, and then maybe there's some beta decay that occur, and then there's a lot of neutrons, and it goes to this closed neutron shell here. But for the S process, because the neutron capture rate is slower in comparison to the beta decay rate, so you can see that whenever it captures some neutrons, the rates are comparable. So it has some beta decay and then neutron capture and beta decay. So it's something like that. The gist is that there should be high density of free neutrons for our process to occur. And here it shows two graphs. So this is one of the graphs, which is the relative abundance as a function of the atomic weight from one of the very famous paper called B2FH paper back in 1957 by Burbage, Fowler, and Hoyle. So here, what is shown is that this atomic weight is roughly the proton and the neutrons added together. And on the right, there is this the Z, which is the atomic number, and the N, the neutron number, fall together. Where here, the black line is what we call the neutron drip line, which is the stable isotopes here. So you can see that as I circle it on with the red one, here this is n equals to 50, here is n equals to 50. What's shown here is that you can see for the S process, which is in green, dark green, is very close to this neutron drip line, you can see. But for the R process, which is in blue, is actually further away from the neutron drip line. So you can see that um, for R, with the same N equals to 50, there's a smaller Z. So that's why it explains there's a shift here. The R has a smaller atomic weight compared to the S process. So there's a shift in this abundance peak, not only in N is equals to 50, but also for N is equals to 82, which corresponds to the one here. So this graph is one of the evidence to show that our process do exist in nature. So I want to talk about what is our process. So what are some of the astrophysical sites that it may occur? Um, so astrophysicists thought that it may occur in core collapse supernovae because when the supernova's core is collapsing, it provides some of the necessary physical conditions for the our process nucleosynthesis to occur. But there's a problem that is it has a very low abundance of our process nuclei. So we physicists still do not are not sure whether it does it occur in the supernovae. Another possible site is that it's in the neutrino-driven wind because what it means by neutrino-driven wind is that um, the as the supernova it has a core collapse and there's an explosion. The protoneutron star cools by releasing tons of neutrinos within seconds. The neutrino interacts with material in the supernova shock. So it means that there are a large number of neutrons per seed, which provides a very, very great physical condition for our process to happen. But there's also the downside, which is the alpha effect, because in this neutrino-driven wind, the protons produced, it can actually capture more neutrons. So you know that for two protons and two neutrons gives you one alpha particle, which in turn reduces the number of neutrons which are needed for this our process to occur. So recently, what scientists have discovered back in 2017 in LIGO is that a neutron star merger. So what I observed was mainly two stuff. So one is hot blue masses of highly radioactive R process matter for atomic number greater than 140, which is strontium. The other thing is some of the cooler red masses of R process nuclei with smaller atomic mass, atomic number smaller than 140, which is rich in actinides. And by the way, this list is not exhaustive, so here I'm only listing three of the possible astrophysical sites. So, what are neutron stars? Neutron stars, they are compact neutron packed cores left over when massive stars die in supernova explosion. It's very dense, so it's like around a billion tons for 1 teaspoon of a neutron star. So you can imagine Mount Fuji in a cup of coffee. It was back in 1974 when astronomers Joe Taylor and Russell Holmes first found a pair and which got them Nobel Prize in physics. And it took them very, very long time, 300 million years to crash into each other. So that means back in 2017, it was so lucky that LIGO captured this data. But actually, uh, 50 years ago, in 1967, the U.S. satellites they actually spotted a flash of gamma radiation. They thought that it was some sort of bomb testing from the USSR, but turns out it was not. So in the early 2000s, LIGO, there was the first light from LIGO, and only after 15 years later, um, this GW data captured in GW170817 using telescopes from a wide range of spectrum, optical, radio, X-ray, gamma ray, IR, or even UV telescopes that it captured the signal of neutron star. And by the way, in also in 2017, LIGO got its Nobel Prize for the observation of GW signal. And according to one of the astrophysicists, Thomas Dent, he described this neutron star merger as emitting some of the most intense and violent radiation of any astrophysical object. So here's one of the simulation of two neutron stars spiraling towards each other. So please take a look. So as you can see that after the neutron star merge and collide, there is a great burst of gamma radiation. And this is how LIGO um detect the signal. So some of the nuclear physics behind, because the our process actually depends on a lot of factors. So I'm gonna briefly mention them. Um, so first is the neutron capture rate. For these theoretical calculations, there are actually a lot of possibility of which kind of theoretical model to use. Uh, for neutron capture rates, they can actually use Hauser-Feshbach statistical decay, which is some sort of Monte Carlo simulation. So this is actually describe the decay of a compound nucleus in statistical equilibrium through the evaporation of particles and photons until a ground state or long-lived isomer is reached. You can see here, this is some of the um, schematic diagram. So at first there's this ground state AZ, and here it shows some of the possible decay path into other forms. And we can actually define channel C with these parameters. And using this, we can put it into a simulation. Also, nuclear masses, if there are experimentally determined masses, it's more preferred. Otherwise, we have to use the theoretical predictions using the nuclear shell model. And for the beta decay rates, by introducing the growth theory, and we use some approximations such as replacing sums into integrals and assuming average values of matrix elements, we can actually determine the beta decay rates. And finally, the fission barrier, because multiple fission cycles they're possible. And after the nuclear fission, the products they can continue to capture the neutrons, which repeat the cycle. So it really depends on which kind of fission cycle that you're using for the calculation, and really affects the theoretical result. So what's next? Um, so after these research, there's still lots of mystery that's left that hasn't been answered. So some of the mystery including such as is the hour process abundance distribution in the solar system the result of one or more or multiple environments? Or what are the roles of individual nuclei and their neutron capture and beta decay rates in determining the final hour process abundances? We still have a lot of questions that hasn't been answered. That's why we still need to observe more signals such as those from neutron star mergers to explain and to know more about what is happening in the R process nucleosynthesis. So here are the references, and thank you so much for listening.